Okay, in regards to the math, how's that coming along?
Good. I was doing some reviewing our uh some problems yesterday.
Hmm.
Just going over the this PDF, trying to see if I can do these on my own, which so far it's going well. And I just do some extra practice, just so I feel more comfortable.
Okay.
Uh, yeah.
Okay, let me see if I can grab that PDF again. And we were talking about some things from question 5, 6, and possibly 7.
Yes.
And if you can go ahead and get your screen shared, perfect. Okay, you might need to zoom out in your browser so you can see everything. If you hold the control and think hit the minus key.
This is okay.
Oh, yep, as long as you can see it.
Okay. Perfect.
Okay, so you said you're okay with question 6, correct?
Yes. I feel like if I were to go over the problem, I think we had a similar problem. Sorry. Like that we went over a couple weeks ago.
Okay.
I think I could do it.
Okay, so let's focus more, I guess, on question 5. Okay, let's just start with the first one there. It says write down, or starts off by saying for x inside of reals, let p of x as predicate correspond to this formula. So write down not p in a form that doesn't involve any negations. What do you remember from your propositional logic?
Honestly, I didn't know that you could write that without negations. I thought the whole point of the symbol next to px is to negate it or write the opposite of what it says. Um,
Yeah, that's true. Um, Now, there's going to be 3 basic operators for you're doing things with propositional logic. You got your negation, you got your conjunction, and you got your disjunction. You can think of it kind of along the lines of like atoms, where you
mhm.
have these 3 basic components and you really can't go any further. Now, you can with atoms, I get that, but just kind of play along. But you would take the different variables, the different terms, combine together and make so-called molecules. You get these so-called logical molecules using those 3 basic types. And
Mhm.
here we do have an existential statement. When
Mhm.
you take a truth and you're negating a truth, if you negate an existential, you're going to get a universal.
Mhm.
And
I
that's
do
kind
remember
of
that.
good, good. And that's kind of what they're referring to here is you want to write things down so you don't have negation. And if you negate for some, that means for all. Right. So if you were to just take this and negate it, and let me take this back here. I'm going to rewrite that. I'm just going to say P implies Q.
Okay.
Okay. Now I'm just kind of curious. How do you go about this problem? What would you do?
Um. Well, honestly, I would just get up to um the part where you just change the for all to there exists
Okay.
a y. Um, in R, I don't think the in R changes, right?
Would you do that? Would you put a line through the so Y is not inside of R?
Mm,
No, you wouldn't.
no.
Okay. So that's sometimes what students who trip up on. Just note that the negation just adheres to the universal quantifier.
Mhm.
And it also is going to adhere to whatever's back here.
Okay.
Okay, now here's a
Oh,
question. Go ahead.
maybe would the inequality flip? I don't know.
Well, there is something that's going to be played out here,
Okay.
but I got a question for you real fast. If I just look at a truth table for a moment, and let's say if I have P, Q, let's say if we have P and Q, and instead of saying T's and F's, let me just say ones and zeros. One for true and zero for false. If you have P implies Q, if you have truth implies truth, that's true. So if I was going to say something along the lines, if you pass the exam, then you will pass the course. So if you study and pass, absolutely, you get the passing grade. If you didn't pass the exam, you're not going to pass the course. And you're not being lied to. You know exactly what's going to happen. Let's say if you pass the exam, but I fail you anyways. Did I lie to you?
Yes.
Absolutely. You got a reason to file a grievance. So that's a lie. What if you don't pass the exam, but you still pass the course?
Is it technically still lying?
No,
Oh.
I'm telling you the truth. I told you if you pass the exam, guaranteed, no questions about it, you're going to pass the course. But I didn't say what would happen if you didn't pass the exam. What this is called right here, that's called grace. It's called mercy. That's called a curve. And these two statements, these are known as vacuously true. It's true by default.
I see.
So whenever you hear that word, that's what they're referring to. There is nothing there. I mean, it's nothing. There, it's false premise to begin with. So whenever you start off with a false premise, the conditional statement's true, regardless of what it's going to be. It's like looking inside the empty set. Purple elephants exist inside the empty set. Prove me wrong. Now, what I want to do is I want to take this and I just want to break it down for a moment. And we said a second ago, you can use negations, conjunctions, and disjunctions, and you can reconstruct any propositional statement. And a conditional statement is one of those propositional statements. So let's just say if I have P or Q. If I have P or Q, you're going to have truth or truth. And if you have an option of truth, always run to the voice of truth. Cling to it. True. If someone tells you a lie and someone tells you the truth, run away from the lie, go to truth. If they're both telling you a lie, though, you're kind of out of luck. It's going to be false. And if look at the conjunction, P and Q, it's only going to be true if both pieces are true. So if true and truth, that's truth. And like Mama always said, you tell me the complete truth, the whole truth, not part of the truth. So if someone tells you part of the truth and still tells you a little bit of a lie, it doesn't matter if it's 99% true, but if you have a little bit of a lie in it, it's false. So this is false, that's false. And two lies, yeah, you put them together, it's still false. And if I look at the negation of P or a negation of Q, here I would have true. Oops, sorry, I would have false. And then true. I'm going to reverse the truth hits. False, since that's true to begin with, and then one, and then zero, then one. And let's say if I looked at the negation of P and Q. So again, I would take a look at this and I would take a look at that. But because I'm conjoining with falsehood, I don't really care about what's happening over here. I know automatically false and false. And likewise, that's false. So that's false. The only time a conjunction is true is when they're both true. So you have that. And let's say I'm looking at not P or Q. Well, for not P, falsehood, falsehood, but there's still a chance. Look over here at Q and see where the truth is. Run to truth. Get away from this piece, go to that piece. So that's true. Here, you're kind of stuck. I mean, there's false and false. There's no other option. It's false. But down here, you see that when we look at the not P, it's true. I don't really care what happens with Q now because I know I have at least someone tell me the truth. Now, I got a quick question for you. Whenever you look at, actually, let me do one more up here. Let's say if we have P and not Q. So again, I have 0 there, 0, so falsehood. So automatically false and false. I don't care what the P, I know I can't have truth is something's going to be a little bit of a lie. And when I look at P, I see down here, those are both going to be false. So I know that that's going to be 0, falsehood again. Here we have this one and we have that. So that's going to be true. Now, here's my question. Whenever you look at the conditional statement here, can you find another row, column in the truth table that has that exact same structure?
Not P or Q.
Right there. So what that tells us is this conditional statement can be recalibrated to look just like that. And this is something called the material implication. P implies Q is logically equivalent to not P or Q. Now, I got a follow-up question. Let's say if I take the negation of P implies Q. If I take the negation, what happens to the truthhood? If it's true, it becomes false. And if it's false, it becomes true. So I would negate this, and that would be false, true, false, false. Is there another row column over here that has that same structure?
Oh, P and not Q.
Absolutely. Now, follow-up question. Whenever you're looking at a conjunction and a disjunction and statement or statement, are they the same thing?
No.
Absolutely. So here's the main question. If you look at a conditional statement, what really is a conditional statement? What's that right there?
It's an or statement.
It's your or statement. It's your disjunction.
Mm.
What about this statement there?
And
It's and. If you take the negation of a conditional statement, is it a conditional statement?
yes, because or an and or
It's not.
conditional statement. Oh.
What we just discovered was a conditional statement is a disjunction. It's an or statement. And if you take the negation of conditional statement, are you getting another or statement?
No.
You're not. And this seems so incredibly wild. It seems strange, doesn't it?
Yeah.
Because the way that we speak in a way that's not really logically rigorous, it's not mathematical. We have a lot of context clues when we're talking to someone that we can put the pieces together to understand what they're really trying to communicate. But when we're talking about mathematically, speaking rigorously, we got to remember that when looking at a if-then statement, it's not a causal explanation. It's not that if I have this, because of that, then I will have this. It has nothing to do with that. If it rains outside and the sidewalk's wet, it doesn't mean that the sidewalk's wet is because it rained outside. It might be for some other reason. So you got to remember this important key detail. And this is where people do mess up because they're so in custom, so ingrained, because that's the way we speak, to say
Mm.
if then negation is another if then. It's not.
Mm.
With that
I had
said, go ahead.
just a question, like a clarifying question.
Mhm.
Um, so when I read a statement like, oh, sorry, when I read a statement like this, right,
Mhm.
that negation is only applied to P, right?
That's correct.
Okay, just so that I don't like include both. And then my other question was gonna be like, do we treat this like a distribution? But obviously you don't.
No, you
I mean,
don't.
you do, but like in the sense that you negate every part of the statement, but only if we're doing like if I'm thinking of traditional distribution, both of them would have that like that symbol, right?
Yeah.
But that's
But
not how it works.
it's not how it works, is it?
Okay, just so that I can keep that in mind.
Good. Hey, those are some great questions. When looking at all different configurations you can make with the different implications. Now, here is your conditional statement. Is there another column that has the exact same structure?
Um, the last one.
Okay. Now, what about this right here? The negation of that. Negation of the conditional. Is there another one up here that has the exact same structure?
Mm, no.
Okay. Now, what about this one right here? Is there another one that has that exact same structure?
Yes, the one right next to it.
Good. Now, this right here, this is known as your conditional or implication. This back here, this is known as your contrapositive. Have you heard that word before?
Yeah.
So we're going to do proofs by contrapositive. This is the structure they're asking you to do. These two also have a special name to it. We could talk about something called the converse and the inverse. Here you go. So
Okay.
the converse is logically equivalent to the inverse. The converse is not the same as the conditional, but the conditional is exactly the same as the contrapositive. And sometimes it is extremely complicated to prove something directly. So we go indirectly by doing a contrapositive or doing a contradiction.
Are those two the same thing or no? Contrapositive and contradiction?
Mm, no,
Okay.
but it is a type of indirect procedure.
Okay.
Okay, now, just to help you remember this a little bit better, give me a second. I want to put this up here. Okay, who's that?
Michael Jackson.
It's Michael Jackson. What's he doing there?
The moonwalk.
Yeah. You know what he's wearing?
Ah.
Converse sneakers. Look at that. What's a Converse do? Flips around, doesn't it?
Yes.
So if you could just kind of remember Michael Jackson doing that moonwalk, hey, maybe he's wearing these Converse sneakers. Just go along with it. You're walking it backwards. You're walking the implication backwards. Q implies P.
Okay.
And for the inverse, what you're going to do is just throw the negation out there, just like that. Kind of like you're thinking about a moment ago where you just distribute the negative. That's just going to be the inverse argument. Okay, now make sure you do remember the contrapositive, converse, and inverse. That's terminology that gets thrown out there quite a bit, especially when you start doing proofs. Okay, now let's go back up to this problem. And if you want to take the negation of the conditional statement, first write the conditional statement in terms of your material implication. So P or Q. Then distribute. When you distribute, you're going to use rules known as De Morgan's laws or De Morgan's rules. It's just like if you have a negative and you distribute it through, you have negative A minus B. De Morgan's rules take the negative, just make it a negation, and you're going to have A, and you say or B, and you're going to say not A, not B. Put the sign and negation of Q. And this would be the negation of the statement above. Okay, now let me grab that statement again. And here we said P is going to correspond to that piece. So what I want to do is just articulate it again. I'll say x squared is going to be greater than y. I'll put the word and out. And I want to make sure when I'm looking at Q, I want to take its negation. So if you negate an inequality, if you say x is bigger than y, the reversal of it is x is less than y or equal. Okay, now we just taken the whole entire phrase and we just recalibrated it so that there is no negation. Okay, let me give you a moment there. Take a look over that and see if it makes sense.
I'm a little confused with the second line. Like, why did this, or where, like, how did we come up with that?
Good question.
If you could repeat it again.
Yeah, sure. Right here. Let's go back to the truth table. What was logically equivalent to the conditional statement?
Oh, the not P or Q.
Right. So basically, I'm going to use that as an expression.
Oh, you're substituting.
Yeah,
okay,
exactly.
Okay. Okay, I get it now.
Good. So one of the key takeaways is this: a conditional statement, when you negate it, I'm sorry, it's not a conditional statement. You turn the disjunction to a conjunction, and you got to be careful with it. Mm-hmm. So as you're going about looking at your negations, my recommendation is take it and write it symbolically first. And after you've written it symbolically, then go through, start applying all these different identities, to which then do whatever you need to do to make it crank out what you need to crank out. Let's just say for the moment, you just want to take these phrases and you just want to recalibrate them symbolically, a little bit more formally. How would you, now there's not just one right answer, there could be several right answers here, but how would you go ahead and recalibrate one so it's stated symbolically in terms of, using quantifiers, existentials, and universals?
So for number one, I like to see that there is. So for me, this is kind of like there exists, maybe. A smallest positive integer. I don't really know how to express smallest, but positive integer would be like if I make the number n, or maybe something including um,
Okay, so what we need is we need to first ask ourselves, what are we talking about? So
yeah.
we need to establish some kind of foundation, some kind of basis. So I need my set of discourse. I need to know where I'm looking.
Mm.
So just like we had beforehand, we had Y instead of R. Let's say something like
Yeah.
N is inside. Now, here's where things get
Integers.
a little bit interesting. Based upon the book that you're using, the convention, you can either say N, the set of natural numbers, it could start off at 0, then 1, then 2, and 3, and 4. You could also start off at 1, then 2, 3, and 4. This is something that's not really well established still to this day. You just have to know what the book is and what your professor is saying N is going to correspond to. Now, a lot of people do start off right here, starting off at 0. So let's just go ahead and take that here for today. And I can say N, and this would be non-negative. And I can also say Z, that'd be all integers. But I'm saying whenever you look inside the bag, you unpick it and you can say such that N is bigger than 0 because I need it to be positive. And in fact, let me write it more like this. And for anything you pick inside the set of natural numbers, and let's just say it's positive, and sometimes notation used, so we don't worry about the 0 issue. Anything you pick inside there, now you can use the vertical line for such that, or you can just say the word such that. N will never, ever, ever, ever exceed M. Or I guess we can get down to the smallest.
Okay.
Can you find a number that has that characteristic? Absolutely. 1. It's the smallest
Yeah.
one out there.
Mm-hmm.
Okay. Now look at the structure in the logic and in the sentence.
Oops. Would this be like an and?
Yeah, that comma right there, right between it, that is talking about an and.
Okay, and then I'm trying to find the P implies Q, or not. Yeah.
Well, you could write it like that. That's definitely possible. But the way that we've written it, we don't have it up here. At least it's not as evident.
Okay. Um.
Now, let's get a step further here. Let's say that we want to do negation of the statement.
Mhm.
So if you negate what you have up here, Sonny, how would you do it?
Um. I would change there exists to for every n
Good.
in n. Uh. Now I change it to an or
Well,
instead of
actually,
an.
you would kind of just leave that alone.
Oh. Okay.
But here,
And there exists an m in n
mhm,
such that uh
and the negation of this inequality is that one.
mm,
So for any integer out there, anything you pick, you can find something that that integer is always going to be bigger than. Well, that's clearly not true because the statement above is true. And when you get truth, you get falsehood. Okay, now think for a second why this is so utterly ridiculous.
Because the statement, we want the smallest positive integer. And I would say that that integer is bigger than, we can find something smaller than it now.
Yeah, anything you pick out there, there's always going to exist something with everything. So for this thing, it works for that something, M. For this, it also works for M. That also works for that, also works for that, also works for that. Everything works for this one particular M. So you're hinging it. It's kind of like saying for any epsilon greater than 0, there's going to exist a delta greater than 0. So it has the exact same structure. Now, the structure is okay here. It's ridiculous because when you come back here, you say, no, wait a second, that doesn't make a lot of sense. Because for anything out there, M is always going to be bigger. What if M was 1? Uh-oh.
There's nothing smaller than that.
Right. Okay, now let's take the negation and let's just see if we can articulate it. And we could do just a strict transliteration. Bad on English, but good on the math. So for any integer n, we can find an integer m such that n is bigger than m. Now, after you went symbolically into it and you take negation of it, you can do a transliteration, just write it in English as fast as you possibly can. Don't worry about if it makes too much sense. And then if you want to, you do a nice little cleanup job next and just make it flow a little bit better. Could you formalize this symbolically? Okay.
There exists at least one.
So what are we talking about?
So we're talking about prime number. We're talking about an even prime number.
Okay, and prime numbers, are they found in the set of rationals or the set of integers?
Integers.
Okay, so let's make sure we know we're looking inside the set of integers then. So you can say there exists maybe an n or an x, whatever you like, inside integers.
It'd be z, right?
Mm-hmm.
Okay.
Now, z would consist of negative, 0, and positive.
Oh, so positive. Wait.
But no, we can definitely
say
say z. That's fine.
Yeah.
And we can say something like such that. Okay, so we got our set out there. And what we need to do is think about how we're going to take this from here.
At least one.
What are the characteristics for being prime?
I thought it was that they're not even, but it says even prime number.
Yeah. Well, one thing you can say is you can say a number x is prime if the only factors for it consist of 1 in itself. And typically we think of x as being positive. We don't want to think about the negative. Okay, I could take that and stick it in here, or I can just go ahead and put the definition in. I can say such that X is prime and what's the other characteristic I need for it?
Oh, it's even.
And one way of how I can represent it is I can use this division notation for 2 divides. So this is how we write it symbolically that says X is even.
Would it be 2? The number?
That's exactly it.
Oh,
2 is
okay.
the only even prime number out there. It's a real interesting
Okay.
number. Now, look at the conjunction. You have P and Q. Okay, so let's say if we're going to negate it, how would you negate this statement?
So for every X in Z,
Mhm. Such that.
Yeah, such that now it's like that.
Well, you don't want to do that
Yeah,
because
this is just like for me. Um,
let's take that arrow out and see the word
uh,
and.
it'd be or.
We'll do that.
Okay.
Okay, so for every X inside Z, such that not P or not Q.
hmm
Now, bonus round. Could you take this statement and write it in terms of a conditional statement?
Yes.
You remember the formula? If you have X implies Y, this is logically equivalent to not X or Y.
Yeah.
Okay, recalibrate that then. How'd you rewrite that?
Um, would it be like that? Oh, right.
Okay, see if that makes sense. You have, again, the formula, not P, not X, X, P. Or sign, implication, implication, Y, 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 not Q. Now, let's articulate this. Let's go ahead and restate this in English. So for any integer, X, and what did P mean?
That X is prime.
So I can say if X is prime, and what's Q?
Um, that 2 goes into X.
And
Or
the
2 divides
negation,
X.
I can say symbolically, you can say use a universal slash negation. You say 2 doesn't divide it. Or if I just want to verbalize it more, if 2 doesn't divide an integer, then I can say it's odd. So which statement's true? It can't both be true. Is it this one or is it this one? One or two.
One.
One's true. Absolutely. Because again, 2 is prime and it's even. So the phrase, if x is prime, then it's odd, that's false. Now, here's something that's really fascinating. I can still take this statement, how we express it as universal, and say for any integer. I can say for x inside z, if x is prime, then x is odd. And I can keep collapsing it down further. I can say an if statement. See, when you use the word if, it is a hidden quantifier. If this, then that. You're not making any exceptions. You're making broad generalizations. And that's what a universal quantifier is. It's a broad generalization. So if statements, they really are quantified in terms of for all. So you can go back and forth. So if someone's going to ask you a question, take a conditional statement and write in terms of a quantified statement. Really easy. Just do what we did right here. We got P implies Q. Just stick it back here in the back and put your set of discourse in the front with the universal quantifier.
Okay.
Good. How you feeling about it so far?
Good. I think I just need to look at the truth table.
Truth tables are good, but they do get cumbersome very quickly when you start getting past 3 variables, because every extra variable is going to take that truth table and double it. So it goes 2, 4, 8, 16, 32. It gets out of control fast. So the truth tables, they establish basic ideas, but after you get past those ideas, you want to start knowing things like the laws of inferences and connecting up those laws, such as the material implication for one, contradiction for another. Sometimes you'll have words such as monus ponus and monus tollens, and like, okay, that's kind of saying injective and surjective. Just tell me what it is. It's implication, contrapositive. That's really what those things are.
Okay.
Go ahead and take a look at one of these problems here. Which one looks interesting to you?
Number 8.
See if you can write that in terms of an existential or universal quantified statement.
Would that be in words, or would that be like with like there exists and for all?
Yeah,
Okay.
yeah, just like that.
Okay.
Now, again, you do have some flexibility of how you write this. You just want to make sure you capture the logic of the statement.
Would it be there exists a polygon? Like
Well,
I don't know.
for this statement, am I making a broad generalization or am I making a particular, for instance?
I think particular, for instance.
Okay, so if it's a particular where it's just happenstance happens once, that it will be an existential. Exactly.
Okay, so
Is that really what's being played out though? No, I know the indefinite article a, it's can sometimes be taken actually in terms of an existential and universal. In this case, it's saying polygons, take the word A out for a second, with three sides are triangles. If you rephrase it that way, can you see the universal statement embedded within the sentence?
Mm, I
Can
think
you
it's sorry.
can can you think of a polygon that has three sides, but it's not a triangle? Now, you can definitely do things like this. That's not a polygon.
Yeah,
You
I
have to
think
close
it
it
does
up.
have to be triangle. Yeah, I think. Yeah. I mean, I agree with the statement.
So, really, what it is, it's a universal statement. And we're
Mm,
making broad generalizations. Polygons, for any polygon, three sides is a triangle. Why don't you try to take this and write this conditionally in terms of implication?
and that would be with like the words. Is that
If
what you mean?
then. Mhm.
Okay, so if polygon has three sides, then it must be a triangle.
Now, when you write in terms of the if then statement, do you see the universal aspect of the problem?
Yeah, like so for every
Yeah.
polygon with three sides.
Yeah. It comes a little more obvious, doesn't it?
I just don't know what I would put here.
Uh, you could say you could say a lot of different things. You can say, let's say for every X, and we'll say P. The thing is, if you say P, you have to just define what P is. It's a set of polygons.
Okay. So we're saying like this particular polygon, like X in the set of polygons?
No, arbitrary, not particular.
Okay.
But for any polygon, if the polygon X has three sides, then X is a triangle.
Mm,
Okay, see if that makes sense.
yeah.
Okay, go ahead and negate it. What's the negation of the statement?
It'd be like there exists an X in P. Um, would it be correct to say like such that? Or
Yeah, you can say such that now if you like.
would I change it? I wouldn't change it, right? I'd just say like there exists an X in a set of polygons such that, or like if it has three sides, then
Okay.
it is not a triangle.
Well, let's put a nice intermediate step up here then. And do you see how you're kind of fixated on the words and you're trying to make sense of the words in your mind?
Mm-hmm.
That's natural to do. But we want to do is break away from it because we don't want to bring things to the table that shouldn't be brought to the table. We don't want to incorporate our bias as we're writing it logically. So what we can do further is we can just say if, and we'll say little p implies little q, or this right here is little p, and this is little q. If you write it more like symbolically and you take negation, you get away from that trap.
Mhm.
And if you take negation, that's a symbol right there for such that, by the way.
Mhm.
If you take negation of the conditional, remember conditional is logically equivalent to not P or Q.
Mhm.
So we have P and not Q. Now, let's take this and let's rewrite this. I can say there's just a polygon and P again. It has three sides. That I can write, I can say and. I can also use the word but, just some kind of conjunction. And if I just want to do transliteration as fast as I can, I can say
Mhm.
and I can say X is not a triangle. The next thing I would do is I might clean it up so it's a little more casual, but still contain the meaning of it. This is kind of hard on the English. It's good on the math. It's hard on the English.
Yeah.
So I might actually use the word but right there instead of and.
Okay.
Okay, but notice what we did again. We took the phrase, we rewritten it symbolically. We took the negation, and in order to avoid the trap of getting locked into the actual phrase and try to make sense of it and try to make sense of it as I'm writing it, it's too
Mhm.
much real estate in your mind. It really is.
Yeah.
We just take it and rewrite it symbolically all the way, apply the algebra, the logical equivalencies, crank it out, and then just reinterpret it back. That way, I don't have that extra complexity up here. I'm just trying to figure it out up here and trying to get down here. These individual steps are going to help.
How are these the same? Like, why wouldn't you just put like
Oh, they're not the same
this?
because when
Oh,
you
okay.
negate, you apply De Morgan's laws, and the negation goes straight on the P. So not is P. Reverse the sign from or to and then negate the Q.
Oh,
So you have not Q.
I guess I was just confused because I thought because the negation was right next to P that it already like was applied, but I guess it's like this, right? Like you haven't applied it yet.
That's right. Not yet.
Oh, okay. Okay. And this is an or, right? P or Q?
Uh, over here on the right. Yeah.
Yeah. Okay.
Okay. So let's go back to your problems you had. The first two. So we did the negation. We hammered it out. We got a good idea now how to approach these kind of problems and how to reinterpret it, rewrite it down, so it doesn't involve any negations. For the next part here, it says, what is the set for all x inside of R? P of x is true. This is where you have to kind of think about, okay, what is this really saying? For any real value, we want to make sure that this is always going to be the case. Whenever you square it, it's bigger than y, where y is going to be any value out there. Okay, so think about that later on and think about different values you can check. Try seeing what would happen, follow the logic. And it's really saying for any x, since there's no limitations on it,
Mm-hmm.
hinge it up for any y, this is going to be true. So if you have this, in order for a conditional statement to be true, we're really looking to see when is the premise is true. I, I don't really care about the vacuous statements for the most part because I know that's always going to be true. It's really seeing what happens here. Okay, so think about that. I want to steal your thunder away from you. Give it a thought and see what it might be for X and Y. Okay, now next time, what we can do is just keep going through question 5. And there was a proof here I want to take a closer look at. It was part 3. Oh, we also did this part too, part 4, by the way. Where you distribute again. Turn implications into the material implication and then crank it out. Okay, so let's look at this right here next time. Looking at that proof and showing that root 3 is going to be an irrational number.
What does this symbolize? Like the symbol?
That's another way that people sometimes write negation. And they do that because look at your
Oh
keyboard.
yeah, that's true.
They don't have that logical symbol on the keyboard, so they use the tilde.
Oh, okay.
I've also seen people do like a complement on top. That's more inclined to sets. I mean, it's pretty much the same thing, but okay, you're kind of stretching it a little bit.
Okay. Perfect.
So why don't you try this one here by yourself later on? Use the material implication and just follow it out. And as soon as you get your answer, why don't you put your answer right here in the bit paper?
Okay.
And we'll take a look at it next time, as well as looking at number 3 in more detail.
All right. Thank you so much.
All right. Well, Sienna, you keep up the good work. I'll see you tomorrow.
All right. Thank you.
All right. Take care.
Bye. You too. Bye.